Ready or not, section 6.5, page 400. Right, triangle trig. This is the trig that you guys learned back in geometry. Right triangle trig is just plain old Sohcahtoa. Another way to write Sohcahtoa is this way. What does Sohcahtoa stand for? So this is our Sohcahtoa. Remember, guys, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. Remember that Sohcahtoa only works for right triangles. Period. End of story. So you have to know for sure it's a right triangle. And so if this is my theta, this would be my opposite side. This is my hypotenuse. What's left is the adjacent side. Second shelf down. So across from theta is the opposite. Across from the 90 is the hypotenuse. What's left is the adjacent. So if I call this little a and little b and little c, then we know that sine of angle theta would be equal to opposite over hypotenuse. Cosine of theta would be equal to adjacent over hypotenuse. Tangent theta would be equal to opposite over adjacent. Simple enough? Now obviously you could do cosecant, secant, and cotangent from these by just taking the reciprocals as well, right? So we're going to use these to solve for missing parts of triangles. So one of the things that we are going to be asked to do is take a triangle. Let's take a nice, simple, easy right triangle that everybody's familiar with. 3, 4, 5, angle A, angle B, angle C. And if we're looking at angle A, which one is the opposite? Which one? 3. Which one's the hypotenuse? Which one's the adjacent? I would label those, guys. It makes it so much easier if you label them opposite, hypotenuse, adjacent. So if we want to find sine of A is going to become what? Opposite over hypotenuse. Cosine of A is what? Adjacent over hypotenuse. Tangent of A? What over what? 3 over 4. Opposite over adjacent. Good. Now what if I wanted cosecant of A? What would that be, since sine is 3/5? 5 over 3. Secant would be what? Cotangent? That's it. Now, what if instead of looking at angle A, we looked at angle B instead? Well, now what switches here? The opposite and the adjacent, because now opposite is 4, adjacent is 3. Does the hypotenuse change? No, because it's always across from the 90-degree angle, and that didn't move. So what would sine of angle B be? Four over 5. What would cosine of B be? 3 over 5. What would tangent of B be? Opposite over adjacent. And then you could do the same thing with the reciprocal functions. So that's your basic right triangle trig. Okay? All right. Now another thing that they can do, guys, is they can give you this picture and ask you to find these things, but maybe they don't give you the 3. So how would we find the 3? Pythagorean theorem. So this would be 4 squared plus b squared equals 5 squared. So b squared is 25 minus 16 is 9, so b is equal to 3. And so now that you know that this is 3, now you could do all these. Okay? Now, sometimes what they're going to do is they're going to do this same kind of thing but what they're going to do is this. Oops. Sorry about that. Didn't realize I never lifted up on the eraser there. Well, that's fine. I can still make this opposite and adjacent. Let's make this B, B, B. And they tell you that this is 1 and this is x. How would we find the missing side? You guys are thinking way too hard. How do we find the missing side? Yeah. We know that a squared plus b squared equals c squared. So a squared plus x squared equals 1, which means that a squared equals what? 1 minus x squared, not x squared minus 1. It's 1 minus x squared. So a would be equal to what? Little a. Square root of 1 minus x squared. Can I simplify that? No, absolutely not. This factors into 1 plus x, 1 minus x. There are no pairs of factors to pull out. Now, if we were dealing with quadrants, we could decide whether it should be positive or negative. But since this is floating around with no quadrant attached to it, we don't need to worry about the plus or minus. So this is going to be the square root of 1 minus x squared, because here it's not a coordinate. Here it's just strictly a length, so it has to be positive. Now, what would sine be equal to? Sine of b. X over 1, which is just x. What would cosine of b be? Square root of 1 minus x squared over 1, which is just equal to the square root of 1 minus x squared. What would tangent of b be? Which simplifies or rationalizes to what? What does it become? X times the square root of 1 minus x squared over 1 minus x squared is correct. Very good. So these would be your tangent, cosine, and sine. Do you guys see how that works? So sometimes you'll run into those type of problems. Okay. That really covers the majority of it. What I do need to talk to you guys about is one last thing, and that is that there is a set of identities that are new to you. And that is, we now have an identity that says that sine of 90 degrees minus theta is equal to cosine of theta. What does that mean? Well, let's stop and think about a right triangle for a minute. Let's say this is theta, and this is beta, and this is our 90-degree angle, and this is little a, little b, little c. Okay? Cosine of theta, this would be my opposite, my hypotenuse, my adjacent. What would cosine of theta be? adjacent over hypotenuse, which is B over C, right? The question is, what would this guy be? Well, you have to stop and just think for a minute, guys. Since we're in a right triangle, what do all three angles add up to? So theta plus beta plus 90 equals 180, right? Subtract 90 from both sides, right? And you get theta plus beta equals 90 degrees. What happens now if I subtract theta from both sides? Do you see that all this is the other angle in the triangle? What is sine of beta equal to? No, because now this is opposite, this is adjacent. Do you see why those two things are equal, guys? The sine of one acute angle in a right triangle is equal to the cosine of the other, because the opposite and adjacent flip-flop. So that's where this identity comes from. Likewise, what do you think is true about cosine of 90 degrees minus theta? It's equal to sine of theta. Right? So the sine of theta is equal to the cosine of the other angle, in this case beta. That's the idea. Well, if you had this in a trig proof, you could take it out and put this in its place. If you had cosine of 30 degrees, cosine of 30 degrees is really cosine of 90 degrees minus 60 degrees, right? Which would really just be sine of what? No, not sine of 30. 90 minus theta, sine of 60. What's the cosine of 30 degrees? We know that from the unit circle. What's the sine of 60 from the unit circle? So what we're really doing here, guys, it's not the most useful identity in the world. What it's really doing is it's laying a foundation for what we're going to notice in the next chapter when we start graphing trig functions. And that is that sine and cosine are the same curve. They're just shifted by 90 degrees. So if you shift it back the correct way, you will find that the two graphs match exactly. Which shouldn't surprise us, because as we go around the unit circle, don't sine and cosine use all the same numbers eventually? Just in different places? Right, but even with the negatives, right? You know, yes, you have negative rad 3 over 2 comma 1/2 somewhere, right? But somewhere the y becomes negative rad 3 over 2 and the cosine becomes 1/2, right? So it shares all the same values, just in different places. So they're just shifted relative to each other. Okay, that's really it. So let me give you guys the homework assignment.